for this CCNA Sunday are these. We want to make sure that we understand Ethernet addresses, how layer 2 learning and forwarding work, and the purpose of VLANs. And I have a few surprises up my sleeve for you too as we discuss these topics. So let's go ahead and bring up a topology, and let's talk about this right here. Boom, boom, boom. All right, let's use this as an example. We talked in our previous session about how traffic moves through a network. And in the big picture, in fact, let me just draw it right here. That'd be fun. Let me get a new layer, and let's imagine Bob. So Bob is our user. Hi, Bob. How are you? And Bob's at his PC. Now, that PC could represent a mobile device. It could represent a laptop, a desktop, virtually anything that's connected to the network. And in a corporate environment, Bob is going to be connected to what's referred to as a layer 2 switch, which is the focus of our content today. So we'll talk more about the layer 2 switch. Let's imagine he's connected to this port right here. We'll call that port number 1. And then on port number 2, we have another device, maybe another PC, PC2 for example. And then another port, another device, and another port, and another device. And I'll just put ETC right here. So if Bob is communicating locally on his network, if he's making a web server request, for example, it's going to go something like this. Let me get out some great colors that I can use to reinforce this as well. It'll be totally worth it. And here we go. All right. All right. So if Bob wants to communicate with, let's go ahead and target PC2. Let's say PC2 is running a web server, or we're just doing, yeah, that works. Let's imagine PC2 or this device is running a web server. So in Bob's computer, what he would do is he would, in his browser, just imagine your favorite browser, you open the browser and you go to the name of that website, or in the case if he knows what the IP address is, he puts the IP address in, presses enter, and then behind the scenes he gets a response. Now, what's actually happening with all that, and we touched on this in the last one, I want to reinforce it as we focus on layer 2, his browser is actually using the services of HTTP in the TCP/IP protocol stack. Or if it's a secure session, he's using HTTPS. Those are two examples of application layer protocols. So Bob, let's talk about Bob for a second. Bob may not know that. He may just realize that I'm going to a website and pressing enter, but behind the scenes, there are application layer services in the TCP/IP protocol stack at work. We'll have a separate section on just that in one of our CCNA Sundays. So continuing down, these application layer protocols are going to be then using some services at the transport layer. And I happen to have it memorized, but HTTP and HTTPS, they both use a protocol called TCP at the transport layer. TCP is the protocol that cares. What do you mean, Keith? It's the protocol that cares. Well, if an application layer service like web services is using TCP at layer 4, TCP wants to make darn sure that the message got delivered. So to do that, it's going to do a little handshake up front with the target between the client and the server. Hey, you want to talk to me? Yes, no. And then it's going to send acknowledgments and checks along the way just to make sure that all the data got there. So we'll have a separate section on layer 4 and transport layer protocols, but that's what TCP does for a living. Now, before Bob's computer, this is all in the mind. I'm going to put this in black. This is in the mind of Bob's computer. Let me back that off once. M-I-N-D. I can spell this. So before Bob spits it out on the wire, Bob's in Bob's computer is doing all this. It's called encapsulation. So it takes the request for the web services. It then adds the TCP information. Then at layer 3, it adds the IP information. So it would be Bob's source IP address and the destination, its IP address for the destination. And then at layer 2, which is what I want to focus on today, it's going to go ahead and add layer 2 information. And that would be an Ethernet. Let me change that color. I want that to be kind of the color of the data link layer. Let's go for this color. In Ethernet, that's going to be the MAC address. And I'd like to pause right there and let's talk about MAC addresses for a moment. What is a MAC address? Why do we care? And it's a good discussion. So in this network right here, I've got a switch and I've got some network devices. I've got this really old PC. I just got out of the closet so I could plug it in for an example. If we wanted to connect this PC to the switch, we would do so just by using an Ethernet cable from the device and going to the switch. Just like that. Ta-da, we have connectivity. If we have another device, this is a little Raspberry Pi, little small computer. If If we wanted to connect it, I'll use this. Forgot I had that on my neck. We can connect this and plug it into the switch for connectivity. Now I'd like to ask a question. I'm going to ask it's not hypothetical yet. It will be eventually, but each of these network devices, the network interface card on this computer, the network interface card on this device, the network interface card on anything connecting to our switches, our switch networks, they all have a very unique 12-digit address. It's 12 digits long. Now, behind the scenes, computers use binary, a lot of ones and zeros, like a light switch. But as humans, we view it as a 12-digit number that's assigned uniquely to this interface, this network interface card on this device. And this computer has a unique layer 2 or MAC address. And the MAC, it stands for, not Apple, but Media Access Control. So the problem is that, well, in fact, you know what? Let's do this. Let me show you how you see and do everything I need to. So here at the command prompt, if we want to see what our burned in layer 2 address is, our Ethernet address, we simply do a show ipconfig, and then we say, that's the problem with working on Cisco gear all morning, show commands. Okay, so I'm on a Windows 10 computer, so the command would be ipconfig. Oh my gosh, I had the words. So, and I'm going to bring it up a little bit. So the command is ipconfig on a Windows computer, and that's showing us the IP address and the mask. And IP addresses, those are layer 3 constructs. Think of an IP address like a combination of a street name, like a network name, and also the actual house number on that street. If we wanted to see the layer 2 address, the Ethernet address, that 12-digit burned-in address, we would use that same command, space, with a /ALL. And that will show us the information here, plus the burned-in address, the layer 2 address on the network interface card. And here it is right here. I'll go ahead and highlight it. Now, one of the beautiful things about layer 2 addresses, Ethernet addresses, MAC addresses like this one right here, is that there are so many different names for it. And this is something I wish somebody had just pointed out to me like a couple, maybe 2.5 decades ago when I was first learning about layer 2 addresses, is that give me a list of all the names. That way if somebody mentions this type of an address, I'm like, oh, that's a layer 2 address. That's an Ethernet address. So let's make a list together of the names. And if you have some recommendations in the chat, go ahead and put those in as well. So here are the names over the years that I've seen this address referred to as. One is shown right here, the physical address. So are you saying, Keith, that if somebody says physical address and they're talking about Ethernet, they're talking about this layer 2 address, this MAC address? The answer is yes. And that brings us to MAC in uppercase, Media Access Control. It's also a layer 2 address. It's the same thing. In fact, we could call this the physical address or the MAC address. We could call it the layer 2 address. That works. We could call it, let's see here, physical, MAC, layer 2. We could call it the Ethernet address. And these are all layer 2, just to get that in our minds as well. So Ethernet address, physical, MAC, layer 2, Ethernet. And the other one, because these are burned in from the factory, when a manufacturer makes a network adapter, they actually put in that unique 12-digit address. And so it is sometimes referred to as a BIA, a burned-in address. And that A is address. The burned-in address. I'll put that in parentheses. So now, if anybody comes to us or we're reading an article or we're discussing a network problem and they talk about a MAC address, a layer 2 address, an Ethernet address, a physical address, we can just realize, oh, they're talking about that 12-digit number, which represents 48 bits in the background, but that 12-digit hexadecimal number that's burned into every network interface card, including this one and the other 11 billion network devices that are out there. So that's what a layer 2 address is, an Ethernet address. And that was one of our objectives, is to make sure we talked about the what is, and you go back to this graphic real quick. What is an Ethernet address? And it is a layer 2 address that is burned into every network interface card. Now, also, network interface cards could be, let me bring up that screen for you. Network interface cards are also referred to as network adapters, network interface cards, network cards. That's just the physical card. Most days they're built into our network devices. And this also applies to wireless. So if your computer has a wireless adapter, it's also the same concept. It's going to have a 12-digit number that is burned in from the factory that is its layer 2 address. All right, let me, all right, I've got my overlay on there. Let's see here. Dun, 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 dun. Where is that? Huh. Not there. Not there. Not there. So I've got an overlay with these hello and we'll begin in a few minutes, and I, for the life of me, can't see where it is on my Painter application. All right, so an Ethernet address, 12 digits long. Now, the next challenge is, why do we care about this? And that is a very, very valid question. And let's take a look at why this might matter. And we'll go back to this analogy with Bob. So back here with Bob, and let me go to this layer right here. Perfect. All right. So if Bob is trying to communicate with PC2, Bob, before he sends that information out on the network, he's got to go ahead and input or implement all that information, including the layer 2 address of PC2, before he spits the bits on the network. So the big question is, well, Bob has a layer 2 address, a source address that's burned into his network interface card, and PC2, or the server, whatever he's talking to, has a layer 2 address. But the big question is, how? How does Bob, because he needs to include it in the data that he's going to be sending, he needs to include that before he sends it. And so the method that Bob's computer is going to use to learn another device on the same local network, to learn its layer 2 address, is a protocol called ARP. And ARP is an acronym for Address Resolution Protocol. And it goes something like this. Let's imagine that you and I are Bob's computer, and we need to find PC2's layer 2 address. So here's what we do. We shout. Yeah, we shout. We say, hey, everybody on the network, I mean everybody, I need to know the layer 2 address associated with, and we give the IP address. And then in response, everybody listens to that. It's kind of a bummer, but everybody listens to it on the network, on that same local network. And then the person who owns that IP address says, oh, that's my IP address. I will respond with my layer 2 address. So ARP is the mechanism for learning when a client on one network needs to find out or discover the layer 2 address of another device on that same network. ARP, Address Resolution Protocol. And you know what I think would be fun? We can do this. I think it'd be fun to actually prove that, because understanding it, it's like, okay, ARP is used. How do we prove that? I think a great way to prove it would be this. Let's go to Bob's computer. Yeah, let's do that. Let's go to Bob's computer. And what we'll do is, as Bob learns layer 2 addresses of other devices on his local network, he's going to go ahead and put those in something called an Arp Cache. And the benefit of an Arp Cache, I'll give you the screen here, my apologies. The benefit of an Arp Cache is that, you're looking at the side of my head, I apologize. The benefit of an Arp Cache with Bob is that Bob can ask for somebody's layer 2 address, and then once that gets that in an Arp Cache. So let's go ahead and let me bring up an environment where we can practice with this. And let me do a refresh here of this. Forget about this entry right here. So effectively, let me bring up another window real quick. Yeah, perfect. So effectively, we're going to do this. We're going to say ARP-D for delete, and then an asterisk. And that's going to say to this computer, please delete any dynamically learned layer 2 addresses you have in the Arp Cache. So we'll press enter, and then we'll hit the up arrow key a couple times. And now he knows about this multicast address, which isn't relative to our conversation, but he does not know about this layer 2 address. And to demonstrate, well, let's talk about this for a moment. If we were to send more traffic from Bob's computer over to that device at .20, Bob's computer would say, oh no, I don't know what the layer 2 address is. I can't put all the pieces together. It'll do an ARP. So Bob's computer on its own will do an ARP request. It'll send it out as a broadcast, like an all points bulletin. Hey, everybody on this local network, if your address is 10.16.0.20, could you do me a favor and respond and tell me what your layer 2 address is? Pretty please. And that's what an ARP request does. So to demonstrate that, let's capture it. On this Windows computer, I've got Wireshark. Wireshark is a free protocol capture program. It copies all the packets that it sees going in and out of the network interface card. And then we can actually take a look and verify ARP's behavior as it discovers and asks and gets a response regarding a layer 2 address that's on the same local network. So let's do that. Let me just hit the up arrow key, make sure we still don't have an ARP entry for it. Good. So we do not at the moment have an entry for 10.16.0.20. And just to put this in context, that is the IP address right here of PC2, 10.16.0.20. And Bob's PC is 10.16.0.10. All right. So let's go ahead and let's capture that traffic. That'll be fun. Maybe go to the right window here. And here's my icon down here for Wireshark. I'll just launch it, and I'll start capturing on the network interface card. Oh, there's gonna be a boatload of traffic on this network segment because there's a lot going on. But I want to focus just on the ARP request as Bob's computer tries to figure out what the layer 2 address is for PC2. So we'll hit the up arrow key a few times. I guess we won't. I guess I'll just do a ping of 10.16.0.20. And in the background, because it's not in the ARP cache, it's going to force an ARP, and then it's going to go ahead and subsequently do the ping request. Ping is simply a network connectivity tool, uses ICMP to test connectivity between us, the device issuing the ping, and the device we're trying to reach. So you'll notice that here, the very first ping had a long timeout, 387 milliseconds. That's a long time compared to 22 milliseconds. That's 22 1,000th of a second. And so anyway, the first one very likely took longer because ARP had to happen. If we do it again, because in the ARP cache, we have a much more constant delay for that first hit. And if we hit the up arrow key a few times and do it ARP-A, there we have our dynamically learned layer 2 address of PC2. And just to confirm, let's go verify that's really PC2's address. I just don't like to leave too much to chance here. So if we look at PC2, and on this little virtual machine, if I do a show IP, there's its IP address of 10.16.0.20, and there's its layer 2 address. And what I do, I just look at the last 4 digits. 6800 is the last 4 digits, and that's what should be in client PC's ARP cache. So we go back to the client PC, yeah, 6800, and it learned that via ARP. Now, if we go back to our protocol analyzer, and I'm going to stop this, stop the madness. And again, there's a lot of activity happening in the background. I've got multiple networks up there. But let's see here. I'm just going to look for the first set of pings, and I'll back it off a little bit. All right there. Okay. So if we look at the details of this packet, which in this capture is packet number 7, and here's the layer 2 information. So in the layer 2 information, the destination address was a broadcast. Now, in this ARP request, here's the problem. Bob's computer doesn't know what the layer 2 address is of PC2. So ARP is simply going to send a broadcast where at layer 2, the destination address is all Fs. That's in hexadecimal. But behind the scenes, it means it's all ones. It's a special reserved address, meaning everybody needs to see this. So Bob's computer sends a broadcast. Everybody on that local network gets it. They all have to take a moment. Another broadcast. Oh, no. They have to open it up. And as they open it up, all the devices that don't have the IP address of 10.16.0.20 say, wasted time. Next frame, please. But PC2, who actually has that layer 2 address or has that IP address, it says, oh, you're looking for my layer 2 address, and it's going to go ahead and do a response. So we open up this packet a little bit. And so here's the source MAC address. This is Bob's computer. Here's the destination address for the ARP request, which is a broadcast. And if we open up the actual ARP request, it says, hey, here's my layer 2 address, says Bob's computer. Here's my IP address, says Bob's computer. And I'm looking for whoever has this IP address, 10.16.0.20, please respond with your layer 2 address. And we won't have to look too far for that because it's going to be very, very close in the output here. In fact, it's in the very next packet, which is our very next frame. We'll talk about that in just a moment, which is number 8. So here we have the reply, and this reply is coming from, let's see here. Yeah, so this reply is coming from the MAC address ending in 6800, which is PC2. It's going to our Windows 7 layer 2 address, which is 8899. And in the payload, in the ARP reply message, here's where the sender is saying, yep, here's my layer 3 address, my IP address, and what you wanted mostly, here's my layer 2 address, which at that point, Bob's PC put that in the cache of its local computer, and it used it for the very next frame where it did the ping request. So when he did the ping request, Bob's computer included that as the destination address at layer 2. So that's how a computer discovers what the layer 2 address is of another device that's on the same local network. All right, so let's go back and take a look at what we've done so far. We've taken a look at, let me bring up a video. We've taken a look at layer 2 addresses. And my question for you is this. Which network interface cards, if we're using Ethernet, which network interface cards have a burned in, ready to go from the factory layer 2 address? Which ones? Like, does this little Raspberry Pi have one for its network interface card? Does this laptop have one that I just pulled off my desk? Sorry, Raspberry Pi, it'll be okay. How about this little mini me version of an ASA firewall? Does it have a layer 2 address on each of its network interface cards? And the answer is yes. Yes, it does. The second question is, how does a client? So if this PC right here wanted to talk to this Raspberry Pi and it didn't know the layer 2 address of this device, how would it find out? Assuming we're running the TCP/IP protocol stack. What would this PC do? What protocol would it use if it needed to learn the layer 2 address of this guy's network interface card? If you're saying, Keith, it's ARP, Address Resolution Protocol, you'd be spot on. So I want to make sure we're covering the topics I wanted to focus on in this CCNA Sunday. This is a critical function that happens on Ethernet networks everywhere. So whether you're running Checkpoint, Juniper, Palo Alto, Cisco, it doesn't matter. If you're running Ethernet, this process of ARP and dynamically learning layer 2 addresses on the same local network, that's how it works. All right, so I want to talk about Ethernet addresses. I want to talk about learning. And the next question I have, in fact, you know what I'd like to do? I'd like to give you a brief history lesson because it's relevant. Back when I started, back in the day, 1980s, we didn't have Ethernet. We didn't. We had a lot of IBM mainframe networks and things like that. And then when local area networks first came out, we used token ring because that's what IBM was pushing at the time for local area network connectivity. So we're not going to talk about token ring other than what I just did. But what we did use is we used something called Ethernet with coax cables. Now, if you're thinking coax cables, you mean like coax TV, coax? Yeah, that's how it started. And here's how it would work. You get this long coax cable with cuts in it and termination points are long cuts in it. I'm sorry. You get coax cable, chunks of it, properly terminated, and then you have these little T connectors and the network adapter cards, instead of having an RJ45 jack like this does, this is an RJ45 jack, kind of looks like that. That's what we use today in Ethernet networks when we're not using fiber, which is right here. But we would take a T connector and it would connect to this barrel connector on the Ethernet card, and then we would daisy chain like a piece of coax from that computer to the next one, to that T connector, and then from that T connector on that machine to another one, and we daisy chain them. You know, back in the day, in the 80s, it was like, oh my gosh, we're networking, woo! And they called that 10 base 2. 10 megabits per second baseband, approximately 200 meters on a good day. But the problem was, if that coax was broken anywhere along the path, it had termination points on the end, you break that cable, or there's a problem with that cable, the whole network goes, what's the word I'm looking for? Oh yeah, down. It's just boom, gone. And so that's a problem. The other problem was that any device that communicated on that coax network, basically every other device had the opportunity to see every single frame of data, everything. So for security, it wasn't good because you send a frame in, this device sends a frame in, and every other device on the network has a chance to, oh, that's cool, what's that? So what we did, we migrated from coax cable, which was really a pain for all those problems I just mentioned, and we went to something called a hub, Hubba Bubba. So with a hub, we have RJ45 connectors, and what we would do is we'd plug all the devices into the hub. So I'm going to take the that computer, plug them in, take the laptop, plug it in, and we'd have all these devices connected to a hub. Now, the benefit of a hub was that if any single cable got cut, the rest of the network, just that one device would lose service, but the rest of the network would still function, which is good. However, the bad news is that the hub was, they call it a dumb hub. Sorry, Mr. Hub. Because what it does is any signals that go into one port, it doesn't have any intelligence about any kind of addresses, like layer 2 addresses. What's that? I don't know. I don't know what that is. So what a hub did was it just takes signals that come in one port and it says, I must forward these bits out every single other port, blah, like a repeater. That's all it did. So the benefit was if we lose one cable, the network still functions. The negative is it's not too secure. Also, because we're sharing the hub effectively, only one device can send at a time. So with coax cables and with Ethernet hubs at layer 1, because it's a physical, a repeating device, we have something called half duplex. Now, if you and I are talking, like we're having a conversation, let's imagine you and I we're grabbing a drink and whatever that drink might be, and we're just having a nice chat. It'd be really great as you and I talk that we could do it half duplex. What does that mean? Well, half duplex means that we both don't talk at the same exact time. I say something, you say uh-huh, or you tell me something, I say uh-huh, and we're going back and forth having a nice, great conversation, you and I. That's half duplex. Well, on a computer network, if we have 20 or 30 or 40 or 100 devices on the network, and they all have to, only one device can talk at a time, that's referred to as half duplex, and it's not very good. So to solve the problem, we came up with another device. I've got several of them very, very close. And, oh, you know what? I'll use this one. We came up with another device, which is known as a switch, a layer 2 switch. And so instead of plugging into a hub, we can plug into a switch. And if you have a home device, like a home wireless router, it usually has like one port that connects out to the internet, and the rest of the ports connect internally to your local network. And those internal ports, those are switched ports. And here's the benefit of layer 2 switching. Somebody had the idea, wouldn't it be great if when this computer or this device sends data into the network that's supposed to go to this PC, let's just forward it just to that PC. Let's not forward the frames to every other device. Let's forward it just to this computer. And then somebody else came up with the thought, well, if this switch is going to make forwarding decisions based on the layer 2 MAC addresses, the physical addresses, the hardware addresses, the Ethernet addresses, this switch has to learn, where those devices live. I mean, how does this switch know that this MAC address with this device is off of this port number 1? And how does this switch know that the MAC address with the laptop is on port number 2? And the answer is the switch learns by listening. What the switch is going to do, the first time that any device sends a frame into the network, that frame is going to include a source and destination layer 2 address. And if it's a broadcast, it'd be a broadcast address. But in either case, in fact, let's take a look at our packet capture, which I think I still have up. Yeah, check this out. So even with this Arp request right here, I'll bring it up full screen there. So with this Arp request, you'll notice that this is Bob's computer. He has his source layer 2 address included as he sends that data into the network. So here's what the switch does. The switch says, oh, I'm going to memorize that layer 2 address, that source address, came in on this port. Maybe it's port like 1/0 or 0/1 or 0/2, whatever port it is. And after a few moments, the switch can memorize and dynamically learn all the layer 2 addresses associated with which ports. So if there's 10, let's say there's 100 devices, and this device needs to send a packet or a frame to this device, it includes this layer 2 address. When this device sends that into the switch says, oh, I know where that layer 2 address is, and it can just forward it, boom, right to that port. It doesn't have to forward it to everybody. It's not going to bother everybody. It just sends it right to the port. So that's how a layer 2 switch, like a multi-layer, this layer 2 switch, how it learns where MAC addresses live by listening to the frames that come in and then saying, oh, I saw a source MAC address of XYZ on this port, and if I ever get a frame destined to that layer 2 address, that's the port I'm going to use. So what have we covered so far? Let's back up a second and take a drink of water. Have I told you I appreciate you being here? I do. It's great to have you. So we've identified that every network interface card on Ethernet, including Wi-Fi, has a layer 2 address that's burned in from the factory. And those layer 2 addresses have multiple names, layer 2 addresses, Ethernet addresses, MAC addresses. Call them what you want. It's all great. We also learned that if computer 1 needs to find out the layer 2 address of computer 2 on the same local network, this only is relevant on the same local network, it's going to go ahead and do an ARP request. So the ARP request goes out as a broadcast. Everybody in that local network listens, and the one that has that layer 3 address associated with the request is going to respond back and say, oh, here's my layer 2 address, which is then cached and used. The third thing that we've just identified is that this layer 2 switch is now memorizing layer 2 addresses. It knows that the MAC address for this device lives off this port because it's listening to these source frames that come in and memorizing or adding those to something called a MAC address table. Yeah, so that's where we're at so far. You know what we should do? I like taking iterative steps and verifying as we go. So we did a protocol capture to verify ARP requests and responses. How would we verify that a switch can go ahead and learn? I've got an idea. Let's do this. Let's go ahead and let's bring up this topology. Yeah, I think this will work. Let's go ahead and use this right here. This is port, let me take a look at my notes. This is port 0/1 on a switch that I have that I'm going to do a demonstration on. And this is port 0/2 that PC2 is on. Bob's computer, I think it ends in 667. Let me take a look. Let me verify that. Oh, 778899. All right. So I will back that off. 778899. That's Bob's last 6 digits of his MAC address on his network interface card. And let's go grab whatever PC2's is. And we can do that just by going over to the switch. Let's go over to, let's go here. All right, so here's PC2, and its MAC address ends in 666800. And I'll document that as well. 666800. 66680. Is that really 666? Oh, I gotta check that again. That can't be right. It is. All right, that was just an accident. That doesn't mean anything. All right, in case you're superstitious, it's just a number. In fact, what I'll do is let's just focus on the last 4 digits for that bad boy, and then then I won't have to feel bad about doing that for anybody. All right, so I'm going to go ahead and just erase this. Let me get out my eraser tool here. Bonk. There we go. So the last 4 digits of this network interface card are that. So if we powered on this switch and let it dynamic and sent some traffic in, the switch should dynamically learn that on port 0/1 is the MAC address of PC1, and off port 0/2, it should dynamically learn the MAC address associated with PC2. So client 1 up here and PC2 off of port 0/2. And to force that, I'm going to show you some stuff. Whenever I like to verify, I like to do it in ways that can be replicated and proven, not just by luck. So let's do this. Go to switch 1. We'll go into configuration mode, interface, gig, and that port is 0/2, and I'm going to do a shutdown. The reason I'm doing that is any MAC addresses that switch had learned on that port 0/2, gone. And then we'll bring it back up, and then we'll go ahead and then we'll take a look at the MAC address table. We'll send some traffic from PC2 and just verify that the switch is dynamically learning the layer 2 address on that port. So let's bring it up. No shutdown. I used to have a Cisco dog, and that's how I taught him to stand. It was the command, no sit, and he would stand. That's not true. I did have a really amazing dog that passed away a couple years ago, but we had different commands for sitting. Although I always think about that when I do no shut. All right, so let's take a look at the MAC address table on a Cisco switch. To see the MAC address table, the dynamically learned MAC address, we use the command show MAC space address, and I'm tabbing that out, address dash table. And here's what it knows about. So I have a lot going on behind the scenes in this lab, but the point here that I want to share with you is that PC2 Let me change the color there. So PC2 is on port gigabit 0/2, and if we look at the dynamically learned addresses, we have nothing yet on port 0/2. And the MAC address for PC2, once we send some traffic in, it should go ahead and the switch should dynamically learn it. Again, this is just to reinforce that the switch, the way it learns where MAC addresses live, is by looking at the source frames from the devices as they come in on their respective ports. All right, so let's hit the up arrow key one more time just to make sure we have nothing for 0/2. Fantastic. And let's go to PC2. So on PC2, it should only take like one ping. Let's go ahead and ping 10.16.0.10. So this is PC2 pinging Bob's computer. And we'll press enter. And you'll notice that the first one, well, these are not rapid response times, but the first one took a little bit longer. You'll see that, 237 milliseconds, which is about a quarter of a second. And that took a lot longer, very likely because it had to do the ARP. And this little virtual machine had to do the ARP. And then as it sent frames into the network, including the broadcast frame, the switch looked at that source MAC address and said, oh, I know where you live now. This MAC address, you live off port 0/2. We can verify that by going to the switch and hitting the up arrow key one time for show MAC space address table. And there it is, right there. 005079666800. That is the layer 2 address of PC2. And over here on gig 0/1, this is the layer 2 address of Bob's computer that it also learned in the same exact manner. So as we take a look at what we've learned so far in our journey in this CCNA Sunday, we've identified layer 2 addresses, where they come from. They're burned in from the factory on network interface cards. They have several different names that we could refer to them as, but arose by any other name still is 12 digits long. It is still an Ethernet address. We learned how a client on the local network can use an Arp request to go ahead and find the layer 2 address of another device on that local network. And if that other device is out there and hears that broadcast, that Arp request, it sends a response. We've now also identified how a layer 2 switch can be used to dynamically learn the layer 2 addresses based on eavesdropping. It's like, oh, I see the source MAC address coming in on port 0/1. It's this address. And it builds that, adds that to its MAC address table. So in the future, any frames that come in, if they're addressed to a MAC address where the switch says, oh, I know where that is, it can make a layer 2 forwarding decision. So it forwards to the correct port based on the layer 2 information. Now, a couple of things I want to point out. One, what happens if a device sends a frame into the network and the switch does not yet have a MAC address table entry for that layer 2 address? Let's talk about what we would do. Let's imagine that we've memorized all these layer 2 addresses off the various ports, and we get this frame in, and this frame is destined for a layer 2 address that we don't know exactly where it is. I would say we could err on the side of caution. And maybe we just squint and say, I'm going to go ahead and I'm going to flood that frame to every other port in the same network. Because that way, if somebody's out there who needs it, they'll get it. So when a switch does not know the layer 2 destination address that it's in a frame, when it receives it, it's going to do, it's called Unicast Flooding. It's basically sending it to every other port in that same network in hopes that, hey, whoever's out there, maybe they'll see it, maybe they'll use it. Good enough. Receives a frame, and it's destined to the broadcast address, which is all F's in hexadecimal. All right, so let me do this. We've talked about a few critical pieces and fun pieces. We've used analogies, we've used examples, we've used demos, and I'd like to put some music on for maybe 30 seconds, 45 seconds, and just take a look at the queue and see if there's any, and I also appreciate everybody who's answering questions for other people. Fantastic. 2 thumbs way, way up. Who has 2 thumbs and really appreciates you answering other people's questions? I do appreciate you. So let me put some music on for like 30 seconds, take a look at the queue, and then I do have one other concept I'd like to introduce to you, and that's the concept of a virtual local area network, or a VLAN. So let me put some music on, and we'll be right back in about 30 seconds. answers to the questions that come up. Also, if those questions aren't answered that you have regarding this topic, which is layer 2 switching and Ethernet addresses and how devices and switches learn about the layers, and we have a network with 300 devices, if one of those devices, just one, does one ARP request, like a broadcast, that means 299 other devices on the network have to say, what's this? It's a broadcast. I guess I better look at it in case there's something important. They open it up. They look at what it is. If it's not applicable, they throw it away. And they say, I can't believe we were bothered. Actually, computers don't have attitudes. But if we have a 300 device network and there's broadcasts, that's a lot of overhead for devices that have to process that. Also, for security, it's not always good to have everybody on one network. Even though it's switching with these guys right here, we have what's called full duplex, meaning they can send, like this device on a switch, it can send and receive at the same time. And these devices and other devices can all send frames at the same time. Because on the back plane of the switch, it's not, buffer is the wrong word, but it's got hardware on the back end that's keeping all those conversations separate. So it's not just only one device can communicate with a layer 2 switch. We can have multiple devices communicating at the same time, and the switch is only forwarding out to the correct port based on the layer 2 destination address if it knows where that is. All right, so let's take a look at a bigger network and a problem with broadcasts. And let me go ahead and bring out another layer. Oh, that's not what I meant to do. There we go. Boom. All right, there we go. So let's imagine that we have this network right here. So this is a switch. And let's imagine we have 100 ports on the left-hand side and 100 ports on the right-hand side. And if one device sends a broadcast, the switch is going to forward that broadcast to all other ports. So one broadcast coming in from one device is going to go to 199 other devices. Sort of like going into a big room and yelling, hey, everybody, I've got an important message for John. And then everybody says, okay, I'm not John. Thanks for wasting my time. But that's how broadcasts work in IPv4 at layer 2. Everybody's got to listen to it. So instead of having just one giant network, the idea is, why not carve this up? In fact, I'll just draw it down here. So this is our switch 1 original. Now I've got myself thinking about original or original. I think that's right. All right, and then we have switch updated. And here's how we could update our network to make it, instead of having one, they call this a broadcast domain. And it's called a broadcast domain because you send a broadcast in and every other device on that network is going to go ahead and receive that broadcast. So it's called a one broadcast domain. And when I think of that, I like to think of an ARP request because it's very real, happens thousands of times every hour on a busier network, maybe more. And so this is one giant broadcast domain. Broadcast goes in, everybody has to listen to it. If we change the rules a little bit, maybe we slice and dice. So we make two separate logical networks. So LAN 1 and let's call this LAN 10 and LAN 20. So if we have 100 ports over here and 100 ports over here, because these are two now different networks, a broadcast going into LAN 10 would only have to bother 99 other devices. And if a broadcast comes into network 20 or LAN 20, it would only have to bother the other 99 devices here instead of all of them. Now, this idea about taking the switch and partitioning it like this is called dun, da, da, da. And this is another thing that I wish somebody had just told me like 2 decades ago, or 2.5 decades ago when I was first starting learning networking, that a VLAN is nothing more than partitioning your switch. It's a layer 2 function. And you're simply putting some of your ports into one VLAN. I'll actually total this out here. VLAN 10, for example, and another set of ports into VLAN 20. And if a broadcast goes in here, a layer 2 broadcast, it's only going to go to these other devices. So we're isolating the networks. Now, on top of this, this is also very important. If we have two VLANs, normally what happens is we have street names, networks, IP networks, which is a layer 3 thing. But it's important to point out here that if we have one switch and all the ports are in the default VLAN, which is VLAN 1, it's also likely going to be one logical IP network, like one street, one network. Once we start carving up these switches and then put the ports, say all these ports in VLAN 10 and all of these ports in VLAN 20 as an example, then we're going to have different IP networks associated with those. Maybe these ports in VLAN 10 we associate with the IP network of 10.16.0 with the 24-bit mask. And maybe VLAN 20 we use 172.16.0 with the 24-bit mask, or some different network. So VLANs are a layer 2 thing. But I'll tell you what, boy, George, it is so common to hear people talk about, oh yeah, that VLAN, this VLAN, and they're referring to IP networks. So I just want to give you a heads up, because we're going to dive more into this in future CCNA Sundays, is that when people talk about a VLAN, if they're not really paying attention to their words, they might mean this IP network that's associated with this VLAN. Because usually there's a 1-to-1 correlation. So if a customer has 10 VLANs, it's also very likely, at least at the CCNA level, that they've got 10 different streets or networks associated with those. So maybe one's 10.1 network, and another's 10.2 and 10.3 and 10.4. But VLANs are definitely a layer 2 construct. We're going to tell the switch to carve out the ports into their respective VLANs. And I think as a sneak peek, I'd like to show you how to do that. So let's do that. It won't take long. Super easy. Let's go back to our... Let me draw another topology here. A simple one. All right. So let's imagine we have switch 1. And we've got port 0/1 and port 0/2 and a whole bunch of other ports. And for the purpose of this demonstration, I've got Bob's PC here at 10.16. Oh yeah, he's at 0.10. And I've got PC2 at 10.16.0.20. And right now, they are both in the default VLAN of VLAN number 1. If we move them over, if we created a new VLAN, let's create VLAN 10. And here, let me show you the syntax to create it. Don't blink. It goes pretty fast. In global configuration mode, you type in VLAN space 10, you press enter, done. Oh, actually, then you type in exit. If you're at the behind the scenes, it actually doesn't create the VLAN until you exit VLAN configuration mode. But if you type in VLAN 10, enter, exit, enter, boom, that VLAN exists. And then to assign these ports to that VLAN, you simply go into interface configuration mode and you just say switch port, mode, access. And I am abbreviating. I'll walk you through the full syntax here in a moment. And switch port, access, VLAN 10. And yeah, I'll tell you, I'll show you the full commands as we do the lab. That makes sense. So right now they're both in VLAN 1. They can both talk to each other. They're in the same broadcast domain. If we move Bob's PC into a different VLAN than what PC2 is in, they won't be able to talk to each other, even if they have the IP addresses from the same subnet. So let's do that. Let's bring it up and we'll configure VLAN 10. We'll put both those devices in it. It'll be fun. Okay. Here's my management computer. I'm logging in. Okay, so one of the questions might be, well, Keith, how do we, you said all the ports are in VLAN 1 by default. They are. You just do a show VLAN brief, and that'll give you a nice bird's eye view. So we've got the default VLAN, which is VLAN 1, right there. And all these ports, including gig 0/1 and 0/2, are all in that VLAN. So if we go to PC2 at the moment, and we do a ping, in fact, I'll hit the up arrow key. So we can ping PC1 right now, no problem. We're both in the same VLAN, easy peasy. But if we go to switch 1, and we create a new VLAN, so we'll just type in VLAN 10, and enter, and then exit. Boom, that VLAN now exists. Now, the reason I just did a do right there is if you're in global configuration mode, or any configuration mode for that matter, and you want to do a show command, the do is a workaround that says, okay, let him do the show command without having to go all the way out of configuration mode. That's all that is. So now I've got this new VLAN. I could also assign it a name if I wanted to, but it's VLAN 10. But the problem is there's no ports. No ports are associated with it. So let's take Bob's PC and put it in. So to do that, we'll go to Bob's port, which is interface gig 0/1. And what we're going to do is switch port mode access. That tells the port that it's an access port, as opposed to a trunk, which we'll cover in our next video. And we need to assign it to the VLAN 10. So the syntax for that is switch port access VLAN 10. And if we do a up arrow key a couple times and do a do show VLAN brief, check this out. Now, gig 0/1 is associated with VLAN 10. Now, our problem is, though, that Bob's PC is in VLAN 10 and PC2 is in VLAN 1 still. So they won't be able to ping each other anymore. We could verify that real quick just by going back to PC2, hitting the up arrow key. It's like, nope, 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 nope. Not going to happen. We could do this all day long. It's not going to happen because they are in different VLANs, and they believe, based on their IP addresses, they're in the same network. So they are not going to get to each other because they're in separate VLANs. So to solve that, we need to add PC2 to that same VLAN. So to do that, we'll go to its port, interface gig. Looking at my notes here, it's gig 0/2. And we could verify that too. Do show MAC address table. Oh, because here we go. That worked. Oh, freak. Show MAC ADD. There we go. It's because I'm in configuration mode. Context sensitive help isn't working for that show command. But anyway, if I wanted to confirm what port it's on, there's its IP address. There's its MAC address. And it's on gig 0/2. That's PC2. Just wanted to verify I'm on the right port. So we'll go to interface gig 0/2. We'll say switch port mode access, which means, hey, you're an access port, as opposed to a trunk, which we'll cover in the next video. And then we'll assign it to the right VLAN. Switch port access VLAN 10. Then we'll do a show VLAN brief. And, oh, wait a sec here. What did I do wrong? Oh, there it is. I was looking for gig 0/2, PC2 are both in the same VLAN. And I'm also going to do this, show spanning tree for VLAN 10. Now, you are not responsible for spanning PC2. We'll hit the up arrow key. And because now PC2 and client PC are both in the same VLAN, it should work. And look at that. I think we had an Arp request there that happened in the background. And that was the extra delay on the initial ping. Well, I'm pretty happy about that. Let's do one last command, show VLAN brief, just to verify. And let's review. Let's review what we've learned in this CCNA Sunday. I had a list of exactly what I wanted to cover. I think we nailed everything. Number 1, Ethernet addresses, layer 2 addresses, burned in. Devices that make forwarding decisions based on that layer 2 address is a layer 2 switch. Say hello to my little friend. It learns those MAC addresses by looking at the source frames as they come in, and it says, oh, you're coming from this source MAC address, I'll associate with that port. In the future, if I see any MAC addresses destined to that layer 2 address, I will forward it. Clients like servers, routers, PCs, Apple devices, Androids, iOS devices, anything that's on the network, if it needs to learn the layer 2 address of another device on that same VLAN, same local network, it's going to use ARP, Address Resolution Protocol. It is a broadcast, and then the response comes back unicast with the information that the client needed. And then we address the problem of VLANs, or the problem of a broadcast domain that's too big. And so to solve that, we take our switch ports and we carve them up into smaller chunks or sections. So maybe 50 or 100 ports we assign to VLAN 10, another 100 to VLAN 20, and then our broadcast domains are smaller. And then each of those VLANs are going to have an associated IP network or street address as well. Yeah. Now, there's a lot of really cool stuff that I'm eager to talk to you about, but not today, because if we start talking about routing between VLANs, we'd be getting into layer 3, and I want to save that. So coming up next Sunday, if you have not already subscribed, do it, please. And next Sunday, for CCNA Sunday, make sure it's not Christmas. Yeah, it's not. Okay. Nobody wants to be here on Christmas. Next Sunday, what we're going to do is we're going to take a look at trunking. What if we need to do VLANs on multiple switches, like switch 1 and switch 2 and switch 3, and we have a client in VLAN 10 here and a client in VLAN 10 on a different switch? How do those switches keep track of which VLAN the traffic is for as it's going between the two switches? The answer is and 802.1q trunk. So we'll take a look at the concepts of trunking, also some demos of how to set it up and verify it as we continue to build on the basic components and pieces inside of CCNA. I also wanted to point out that these concepts are really helpful, not just for configuring, like I need to configure a VLAN, or they're also really helpful in troubleshooting. The better we understand how these components work, not only are we going to be able to configure it, but the troubleshooting, most of them, I would say a large portion of the IT engineer's job and the IT technician's job is troubleshooting. It's like, why isn't this working as it should? So if we know the commands to look at the layer 2 addresses on a PC, for example, on a Windows machine it would be ipconfig on /all. On a Linux box or a Macintosh as a command line, it would be ifconfig. On a Cisco router or switch, if it had a layer 3 interface, it would be show interface. That could show us the layer 2 information. On the switches, if we want to verify the MAC address table, it's show MAC space address dash table, so we can see what those MAC addresses are. And those are all really helpful. Now, if this is your first pass at learning about layer 2 and MAC addresses, I'm so happy to be part of your journey. If you want more information on layer 2, there's a couple options that are really good. One is you can certainly ask questions in the group here on the channel. I'd be happy to answer those and other people as well, so thank you for those responses. The other options are DevNet. Now, DevNet is the DevNet Associate is a relatively new certification from Cisco Systems, and we created the whole course at CBT Nuggets. It's really good, and most of it deals with programming. So you might say, well, how is a course on programming and network automation, how is that going to help me learn layer 2? Well, I created this little section called Network Fundamentals inside of DevNet, and what it does, it does a very concise job of the protocol stack, what happens at layer 2, what happens at layer 3, what happens at layer 4, and the application layer, and it's all nice consumable chunks. So if you liked what you saw here, you'll love what you're going to see there, and it can help reinforce what we've talked about. And it's live, it's on site today. So if you have a subscription at CBT Nuggets, great. If you don't, I'll put a link, and you can go out there and get a free 7-day trial, and you can probably easily consume all of those videos on network fundamentals from DevNet in 7 days. Easy, easy, easy. And coming soon, the full CCNA playlist for 200-301, that'll be out as well. And it's got more information on switching and VLANs and trunking as well that you can brush up once that's released. Okay, so that's it. Next week, same bat time, same bat channel, we'll focus on trunking. I'll have some demos. I'll help you understand why it's important, how it works, and then we'll demonstrate setting it up. Also on Wednesdays, 4 p.m., if you follow me on social, I also have a live stream dealing with various topics from CCNA to augment it as well. So whether you want to join me on Wednesdays and Sundays, or just Sundays, or just Wednesdays, the key is I want to keep you learning and keeping you having fun.